Hello again, everybody, and welcome back. We're starting a new chapter, Chapter 8 in Honors Physics, and this is going to be on potential energy and conservation of energy. And this is actually kind of an extension of our last chapter. If you recall, the previous chapter was on kinetic energy and work, that is being kind of two parts of the same coin. This is an extension of that, potential energy, and this whole idea of the conservation of energy. So as we start, probably the first thing we need to be able to do is to define what we mean by conservative. This has nothing to do with any kind of political affiliation, but the word conservative, well, think of things that are conserved. If you conserve electricity or if you conserve resources like recyclable stuff, what are you doing? You're accounting for all of it. You're not letting any be wasted. And that's exactly what's happening here with conservative forces, or you can say conservative work or energy that takes place. It's not lost. If work is done, it's stored in some form and can be regained later in a different form. All right. Non-conservative forces or non-conservative work or energy are those types that you might have some energy loss or some forces that are wasted that you aren't able to get back. They're at least not readily able to get back. So we're going to talk about two different examples, and I think that'll be evident a little bit later on as to what we mean by conservative and non-conservative. But conservative means everything's accounted for, and non-conservative means that some stuff is lost in the process. Some forces or some work or some energy is lost. Just as a real kind of a quick analogy, you could say a conservative force, a great one we're going to talk about, is going to be gravity. All right, gravity, G, the gravity acting on a mass. All right, if you put work into that, if you lift a mass up a certain distance, you've done work on it, and now that is going to be ready to do work for you. Once you let it go, it will plummet to the ground and do work on, I don't know, crushing a soda can or something like that. All right, you do work against gravity, gravity does work for you. All that work, all the energy is conserved. On the other hand, a non-conservative force or non-conservative work or energy that is done that we're going to talk about, a great example of that is friction. If you do work against friction, so you have this box right here, okay, and you apply a force in this direction to cause that box to move, all right, friction is acting against you the whole time. All right, so you're working against friction, or friction is working against you. But once you've moved this box over to this point right here, so you put some work into it. Just because you put work into, put work against friction, it doesn't mean friction is now ready to do work for you like gravity. Oh no, friction always acts against the direction of motion. So friction creates lost energy or lost work. And many times we see friction expending energy or work in different forms that you can't get back. Your brakes in your car work on friction. All right? A lot of times your brakes will, especially if you see race cars, you see them light up. They get so hot from all the friction that they actually emit light. That's energy. That's lost energy that you can't get back readily. A lot of times your brakes will squeak or squeal. They shouldn't, but if they do, that is energy also being lost. Or especially heat. You should probably know that brakes do get hot. So if you've been using your brakes a lot, don't immediately take the wheel off and touch them because they're going to be very hot. All right, all these are energy that is lost or turned into a different form that we can't readily get back. And so a non-conservative force, a great example of that is friction. And that is forces that create work or energy that is lost and that is not easily able to be gotten back. Okay? I know I mentioned a few of these already. Conservative forces, gravity, of course. You work against gravity, gravity will now do work for you. You work against a spring, you compress a spring, the spring is going to be ready to do work for you. If you ever, as a kid had like a dart gun or something like that where you put the dart and you compress the spring, it's now ready to do work for you when we pull that trigger and it shoots that suction cup dart out. We're not going to talk about electric or magnetic forces, but if you do work against a magnetic force, it will be ready to do work for you. All these are conservative. Non-conservative forces, friction, that's a big one. All right, internal friction. Tension in the rope. Now, tension basically acts in pairs, but it's not a force that will be able to do work for you later on. Your muscles, they do work. They can actually apply force in a certain direction, but just because you do work against your muscle doesn't mean now it's ready to spring back. Motors and muscles require an external fuel to actually run. So these are forces that create work or energy that require energy from elsewhere that aren't ready to. These forces aren't ready to do work for you, like gravity is. So gravity and spring is a great example of conservative things that create conservative forces. Friction is a great example of one that is a non-conservative force. All right, so what we have here, we're going to have this diagram and another diagram that's similar to it that shows an object moving in a certain path. All right, now from this point of view, we are looking at it from, we'll say, the side. All right, from the side. This is the ground. I'll draw it in black right here. This is the ground. Okay. So you are moving this thing. Where do we start it? At A, right here. We're moving it over from A to B, up from B to C, over back again from C to D, and back down again to A. All right? If we start right here in the lower left, if we start there and finish there, if we complete this path over and up and then over and down, the total work that is done is 0. That is, if you take an object and you move it, you could even move it in a crazy, path, and you bring it back all the way back to this point right here. If you move it in some path but return to the same point, it's a conservative force. You're doing work against a conservative force if all that work adds up to 0. Adds up to 0. Because what's happening here is, look at from A to B, right here. First of all, what force are you applying? You're applying an upwards force, what we call the normal force, right? So you're applying the normal force upwards to counteract gravity. So there is your force that's applied, but your direction of motion is sideways. And since they're at right angles to each other, you can say that that angle right in there, in here, that's your phi, right? There's your applied upward force. There's your direction of motion. Cosine of 90 degrees is 0. So from here to here, even though you may be applying a force upwards, you're moving it in a sideways direction, so there's no work done right here. But here, definitely there's going to be work done because you've got a force applied upwards. That's your normal force, much like right there. Okay, and you're moving upwards, so you're doing work upwards against gravity. Our equation right here, by the way, is calculating the work that gravity is doing. I'm calculating the work that we are doing against gravity. It's going to come out to be the same thing. But here, gravity is acting downwards, right? So gravity is acting in the negative direction. I'll draw a little arrow like that. That's our gravity, or mg, I should say. We are applying the normal force up. So we're always doing work against gravity, and gravity is always working against us. But if you return to the same spot right here, it's all going to add up to 0. So I'm going to say for us, the work that we're done is the normal force. So for us, that's going to be 0 plus mg times the height. All right. In fact, I'm going to leave the h off. I'm going to just say d again because we're used to talking about the work done as being a force times the distance, mgd. And so since the applied force, the normal force, mg, is in the same direction of motion, the cosine of 0 degrees is 1, so there's just going to be m times g times d. Okay? We'll close that up right there. All right, what about from here to here? From C to D? Well, again, we're applying an upward force. The normal force is going to be mg right there. But again, the angle between our applied force and the direction of motion, phi, is 90 degrees, and the cosine of 90 degrees as we move from here to here is 0. And so there's no force done, no work being done right there until we get to this last segment right here. So we go from D back to A. We're applying our force upwards, our normal force equals mg. But the direction of motion, I'll kind of draw that in there as green. All right, the direction of motion that way is 180 degrees opposite. So our angle between our applied force and our direction of motion, phi, equals 180. So that's negative. Cosine of 180 is negative 1. So our last little bit right here is negative mg times distance. If we add all these up right here, 0 plus something plus 0 plus negative something, it adds up to 0. All right, regardless of what the path is. As long as we come back to the same point right there, the work is conservative if it adds up to 0. So gravity is a conservative force. You do work perpendicular to gravity, nothing happens. But you do work against gravity, okay. Now you're doing work perpendicular to gravity, nothing happens. But now you apply a force and then you kind of do work and then gravity, you're moving in the direction of gravity. That results in a negative sign right there, so everything adds up to 0. So the same thing is true of springs. Springs, if you do work against a spring, at some point spring is going to do work for you. But both springs and gravity are great examples of conservative forces. To finish out this little segment, I realize I'm already at 10 minutes. I'll try to keep it under 15. We're going to define how this differs with a non-conservative force. All right, so we're going to same type diagram, and it looks the same, but it's overhead. It's overhead. So we're looking down on the ground, and this object is being moved around kind of in a square path. All right, we're starting at A once again. Do I have the right color? No, let's start with red. All right, we're starting there, and we're going over to B, and then up to C, and then up to D, and then back to A again. All right, friction is the force. Friction equals what? Well, it's our kinetic friction, I should say. It's the coefficient of kinetic friction times the normal force, which is mg, right? So in all these cases right here, the friction is acting against our direction of motion. So we're moving from A to B, but look, friction is acting against us. What's the angle between the friction force and the direction of motion? That's 180 degrees. All right, cosine of 180 degrees is -1. But look at this one, though. We're going from B to C. We're not moving up or down. Remember, we're looking kind of down on the floor right here from overhead. So the box isn't moving up or down. It's just kind of changed direction on a horizontal floor. So the direction of motion is from B to C. But you'll notice that the friction force is against the direction of motion. So once again, phi equals 180 degrees as well. Same thing with C to D. Direction of motion, C to D. Applied friction force, and 180 degree opposite. 180, and you see where this is going with part from D back to A, moving from here to here. Okay, that's your direction of motion, but friction is acting against. So once again, FK, we've got our phi is 180 degrees. All these 180 degree phis means a cosine of 180, -1, -1, -1, and -1. So that's why we have all these negative signs out front. Negative coefficient times mg times the distance. So the work done is our force. So here's our force right here, and then here's our distance. But since these are all negative, they don't add up to 0. They keep getting more and more negative. So if we add all these up, it winds up to be 4 coefficient of friction times mg times our distance. And that is definitely not a conservative force because we're winding up with a negative value. If you move this box all around the floor right here back to the same point, you've moved it some distance, you've applied a force over some distance, but friction has acted against you that whole time, and so friction has wasted some of the force that you applied into moving that box around. All right, so if you move something back to the same position and it doesn't add up to 0, then that means you've acted against, or you've been dealing with a non-conservative force. And friction is a great example of that, non-conservative force. So from A to B, we have 3 different paths right here. It doesn't matter how long the path is. If we've got a conservative force, all right, between A and B, there's some difference in energy state between A and B. And regardless of the path you take, whether it's this crazy path right here or this purple one or this loopy green one right here, it doesn't matter. If you're dealing with a conservative force, the path is irrelevant. All that force cares about is the difference in, you might say, energy state between the beginning point and the end point. So if you're picking up a box and you're moving it against gravity, and you go up and then down, and then over, and then up and down, and whatever, what have you. You end up at some point right here. You're going to get the same amount of work if you do any kind of crazy path between A and B. So the main point, the main takeaway for this section is that with conservative forces, the path, the direction of motion between 2 points is completely independent of how much energy or work is done, if you are dealing with a conservative force and conservative work and energy that is done. Okay, so that's the end of our beginning section on kind of our definitions of conservative and non-conservative. Next section, we're going to be getting into some examples, or the next video segments we are. But for now, I'll just thank you for checking in, and if you have any questions, make sure you see me, and I'll be glad to help you out. Thanks for following along. I'll see you on the next one.